Hello guys, welcome back to my YouTube channel, Gamma Die Gamma. I know it's been a long, unexpected hiatus, but I'm here now finally, and I'm going to make a video about a very interesting theorem that I found on another YouTuber's YouTube channel, and I would like to share that with you because I found it was quite simple but also quite powerful. So, as usual, let's get started. So the setup here is that we have this object here. Uh, the object is a quadrilateral. It looks complicated because I didn't draw the diagram for you all from the beginning. But let me try to break it down. We have, let's pick a color. We have these points A, B, C, D on a quadrilateral, which you can clearly see from here. And we would like to first mark these points. So A is at the origin, which is 0 0. B is P0, it's on the x-axis. Now C is at some arbitrary point QR. D is likewise at some arbitrary point ST. Now the setup is that we have this quadrilateral ABCD, and what we do is we take each side and make a square out of each of those sides. So take side AB and construct the square ABFE, for example. And likewise, do that for all the sides. The theorem says that if we connect these midpoints of all of these squares, so in the sense that if we connect the midpoint of this opposite square to the square that's of the side that's facing it, like that, and if we connect this midpoint to this one, the theorem states that these red lines intersect at 90 degrees. In other words, they're perpendicular to one another. Now, how are we going to prove this? Well, what I'm going to do is I'm going to this first of all, let's, before we get ahead of ourselves, this theorem is called Van Aubel's theorem. And I apologize for my pronunciation. I realize it's Dutch and it's probably Van Aubel or something like that. So I apologize in advance. The method I'm going to use here, I'm going to use vectors. There's another way of doing it, which is complex numbers. But again, since complex numbers, C is isomorphic to R2, which is it can be considered as a vector space with an inner product, the Euclidean inner product. The two methods are equivalent. So what am I going to do for that? Well, what I'm going to do is I'm going to find the coordinates of the point N. I'm going to find the coordinates of the point P, make a line, make a vector out of them, and then sort of show that the dot product of that of vector Pn with vector Mo is 0. Okay, so for that, yeah, I was looking for the pointer. I found it finally. Anyways, so to proceed, let us work each of these points out. So first, if we look at the vector BC, we want to find the coordinates of n. N is here. So if we look at vector BC, and if we think of vector BC as point C, coordinates of point C minus coordinates of point B, I think of it as head minus tail. We're gonna get let's see, q minus p r, those are the coordinates. Okay, and then if we try to do that with bg now, bg is perpendicular to bc because it's a square, and we said in the construction that this is a square. So bg is perpendicular, so the dot product of bc and bg should be 0. And one way of doing it, now it doesn't matter, the orientation doesn't matter, because that will only flip the direction of the vector this way or this way. So bg, we have to ensure that the dot product is 0. So what we do is the x component of bg is the y component of bc, which is r. And then for the y component of bg, we just take the negative x component of bc, which will be p minus q. Now you can see by computation, and the computation is simple, that the dot product will indeed be 0. So this, what I'm doing here for this one side, is sort of going to follow for all other sides. I'm just doing it now so that you should know what's going on. Now point G, what are the coordinates of point G? Well, point G can be derived from vector BG, because vector BG is actually the coordinates of point G minus coordinates of point B. So if we add the coordinates of point B to the vector BG, we're going to get G. So G is just add BG and the coordinates of a vector of point B. So we're going to get P plus R and P minus Q as it is. Now we know G, we know C. This point N is actually, it's the center of the square, and the center of the square is actually the midpoint of the diagonal. Now CG is going to be the diagonal. Point N is going to be at the center of that diagonal line. So we can just use midpoint theorem to find the coordinates of the point N, which is the center of the square formed from side BC. So when we do that, what we're going to do is we're going to add coordinates of point G plus coordinates of point C, and then divide each of those coordinate components by 2. That's the midpoint theorem. So when we do that, we're going to have P plus R plus Q by 2 and negative Q plus R plus P divided by 2. Okay, that's very good. We know N. We sort of done 1/4 of the entire thing. Now, if we repeat this procedure on, let's say, we repeat this procedure on the top side now, this side. Now I'm going to go through it a little fast, because it's literally the same procedure. What you do is you take this, you find the vector for this CD, you find the vector for CI, which is perpendicular to CD. Then you add the coordinates of C, so that you get the coordinates of I. Use the midpoint theorem on the diagonal DI to get the coordinates of O. That's basically the sort of the algorithm for this entire proof. So I'm just going to do this fast. You can check your answer if you're pausing the video and sort of working it out yourself. So S minus Q T minus R, which is coordinates of D minus coordinates of C. You can check that. And we have CI, which is T minus R Q minus S, which is the orthogonal to CD. Then I can be found by adding the coordinates of C, R plus Q minus S, and then O is actually the midpoint of the diagonal DI. So now we just have to add coordinates of d to I and then divide each component by 2 by midpoint theorem, which will give us q plus t minus r plus s over 2, t plus r plus q minus s over 2, and then bracket that out. Okay, that's point O. Now we can do that for side dA. Now dA is this leftmost side. Similar procedure. I will change the color, but I'm not gonna explain too much. Just gonna write the values down. So this is minus s minus t, that's dA. Now d vector dk is negative ts, the orthogonal. K, we can just add d, is s minus t, t plus s. And then p is the midpoint of ka. If you look at the diagram again, and it will be s minus t over 2, s plus t over 2. And now for the bottommost side, it's quite simple, because you see a is the origin, b is on the x-axis, and then e is on the y-axis. So the coordinates of this point, actually of point E, are 0 comma minus p. And then using the midpoint here and then midpoint here, we can or even taking the diagonal and then taking the midpoint, the diagonal be E and then taking the midpoint, we can easily find m. We don't have to do the entire procedure. It's kind of evident. For that simple case, we will find that m is actually p by 2 negative p by 2. Now all that's left is to construct the final vectors that we need. We need mo and we need pn. So mo is coordinates of o minus coordinates of m. And when we do that, because we've found all those points, we get this component for the x, and then t plus r plus q minus s plus p divided by 2, and pn is going to be s minus 2 minus p minus r minus q by 2, and s plus t plus q minus r minus p by 2. And then all we need to confirm is that this dot product is actually 0, because that proves, because if this vector has dots into this vector to give 0, then we know that the angle subtended between them, the theta, has to be 0, because the dot product has magnitude of the first vector times magnitude of the second vector times the cosine of the angle between the vectors. So if there's 0 and the magnitudes can't be 0, it means the cosine will have to be 0, which only happens when the angle between them is pi over 2. So angle between them is pi over 2. In other words, MO is perpendicular to NP, which is basically what we had to show for Van Aubel's theorem. I hope you enjoyed this video. Please let me know if you have any questions in the comment section. I know I kind of went over this a little fast in the end, but it's literally the same formula as before. You can try this with complex numbers instead of writing this as a tuple of x comma y points in R2. You can write that as a complex number a plus ib, where you just replace the y component by a b times the imaginary unit I. And that's this video, guys. I'll try to be more regular. I won't make any promises of how frequent I'm gonna be, but Gamma Di Gamma is always here for you. Let me know if you have any recommendations or anything, and stay home, stay safe, keep doing math, and peace out.